can you see my screen now? Yes. Okay. Thanks. Good. Yeah. So yeah. Just see the time. It's 6 past. So we have until 45 past the slot reserved. So I will try to contain the talk within 30 minutes. And again, I encourage you to interrupt me through the talk whenever something is not clear or you want to know more about. Let's keep it as a discussion. And it doesn't matter if I'm not able to cover all the material that I have prepared. As I mentioned in the beginning, I have material for 2 talks. So I believe it's fine just to keep it slow in the interest of understanding. And later on, if there is interest, we can schedule another talk. So I would definitely be happy to do this. Okay, so the topic of this talk is ZK-friendly hash functions with a focus on anemoid permutations and jive compression mode. So specifically, the work on anemoid and jive is joint work with my co-authors Clemens, Pierre, Pirus, Leo, Robin, and Dani. So they are all distributed across different countries and research and industry institutions. And this is the plan that I have for the whole material that I want to present to you. But today, most probably, we won't have time for everything. But the first 2 bullet points. So the first bullet point is just a general overview. It's actually a motivation. Why do we need new cryptographic primitives such as zero-knowledge friendly hash functions? And I also do some comparison to classical symmetric key designs in order also to stress this motivation. And then in the second bullet point, I will highlight some existing zero-knowledge friendly designs. And at the end of the second part, I will give a taste of anemoid, like our approach to anemoid. And then the third part is wholly dedicated to anemoid, where I go to more details of the actual design, the components, the design decisions, and it's also probably the most technical part. So I expect we won't have time for the third part, or I may at least just give you a taste of it, but probably not cover everything. Okay, so a bit of motivation. So zero-knowledge designs, also like technically called arithmetization-oriented designs versus classical designs. When I say design, I mean hash functions for the sake of this presentation. So I give here a brief comparison. On the left-hand side, you have the classical case. So in classical hash functions, we are working over binary field f2 to the n, where n would be a small number, so typically 4 or 8, meaning that we are operating on blocks of 4 or 8 bits of data. And the operations we are performing are logical operations, each of them corresponding to a CPU instruction typically. So we have modular addition, we have exclusive OR, we have bitwise rotations and shift, and each of them has its own CPU instruction. So it can be like a design can be targeted to be efficient against those. Now, conversely, on the right-hand side, you see the arithmetization-oriented world. So there we're working over fields of large size. So we work typically over fields FQ, where Q would be either a binary field equal to 2 to the n for a large value of n, or a prime. So in either case, Q would be a large number. And the operations we're performing here are large finite field arithmetic. So we're working over big integers. And just as an example, in the classical world, a good example, we say, yes, the advanced encryption standard, it works over f2 to the n, where n is 8. So the smallest block of data that it's processing are bytes, so 8-bit blocks, and that's the input to the S blocks. And on the right-hand side, a typical prime field we are working in, for example, for the BLS12381 curve, the modulus of the scalar field is P listed here. So this huge number given here in decimal. So already you can see the huge gap between the two worlds. Furthermore, we also require some new properties. So in the classical setting, we will be having, so I've generically denoted this as E, where E can be a block cipher or a hash function, but think of it as a hash function for this presentation. So, and we are interested in computing E over some input X. So for example, we want to hash X to produce the hash value Y. And then we are optimizing, so we have an algorithm to do this computation, and we are optimizing it for software or hardware. And on the arithmetization-oriented side, beside this computation, so doing the computation forward, going from X to Y, we are also interested in verifying that given X and Y, indeed Y was produced as the application of this function E over X. So we need this additional element of verifying that the two values respect some computation. And those arithmetization-oriented functions, they're optimized for use in advanced cryptographic protocols. So zero knowledge in particular, but also multi-party computation and fully homomorphic encryption. So here we are not so much focused on like optimizing for software and hardware, but for integration with these protocols. And I will give a bit more details about what do we mean by this optimization. So any maybe question at this? Yes.
I mean, eventually you're going to want to optimize for hardware and software, right? Like at some, right? Like, is that, am I missing something?
Yes. Eventually you want to implement it, of course, into like a running code, right? But let's say that's not your not your primary objective. So in the next slide, I believe it's the next slide. I'll talk a bit more about what we mean by optimizing for these these protocols. Any other comments at this stage or questions? So yeah, so what does it mean to be efficient for zero knowledge proofs, for example? And it really depends. So you can think about efficiency in different terms. Like we want a small proof, we want a fast verifier or a fast prover or both. But more generically, we want the arithmetic circuit that implements our computation to be to have the smallest number of constraints. So the metric is the smallest number of constraints. And what does it mean? So what do we mean by constraints? This also depends on the system within which we are measuring the constraints. So one of the arguably probably the oldest or probably the most popular ones are rank one constraint system. For this particular system of measuring constraints, a constraint is a multiplication. So we want a circuit to be represented with as little as possible multiplications. And as a simple example, if you are given this function, so y is computed as ax plus b cubed times cx plus d plus ex for some constants a, b, c, d, and t. Now you can split this computation into a trace, a very simple atomic operation. So scalar multiplication a times x, then an addition, another multiplication, and notice that each of those operations it always takes two operands to produce an output. And in the terms of the R1 CS constraint system, all those operations that we perform in order to do this computation, we only care about the multiplications. So now this brings me back to efficiencies. So suppose you've designed your ZK-friendly hash function, and you want to argue how efficient it is, or to compare it against other designs. Then, like naively speaking, at a high level, you would represent the operation of the hash function in terms of those simple atomic operations. So you end up with a very long trace of those operations. And thus you build a system of R1 CS constraints, and you're counting the number of multiplications that you are using to do your computation. So smaller number means more efficient under those terms.
Vaseline, the image I have in my head is of algorithms for matrix multiplication, how it's supposed to be like an n cubed operation, but you can find algorithms that bring it down and down and down, which means that you know, like the hardware, when you run millions and millions of these things for a neural network, right? It really shortens the time. That's the image I have in my head of matrix multiplication. Am I far off?
Yes, so for matrix multiplication, I don't know. So there you can have some algorithmic advancements that will give you a faster way to compute it. But here it's more about designing a computation that will do the work for you. For example, produce a hash with as little as possible of those expensive operations. So in this example, these multiplications. So it's more about, like, you want to design your algorithm in such a way that it will impose smaller number of those constraints.
Okay.
So not sure about the analogy with the matrix multiplication, but hopefully I could give a hint.
Yeah.
Okay. Any more comments, questions? So where are ZK-friendly hash functions used? So broadly speaking, we have two applications of them in zero-knowledge protocols. One is as a random oracle. So, for example, in signature schemes, where you need to sign a piece of data, like a transaction, a message, instead of signing the whole data, you are first hashing it, and then you're signing the hash in order to make the signature more efficient. So that's one place where you would be using a hash function. Then you have the Fiat-Shamir heuristic, which is transforming zero-knowledge proof protocol from interactive to non-interactive. So from an interactive exchange between two parties into a non-interactive protocol where the two parties just exchange a single message, maybe the proof. And in that transform, you are also extensively using hash functions, or for example, proof of knowledge of a preimage. So you want to prove that you know the preimage of a certain hash without revealing this preimage. For example, proof of coin ownership in Zcash. These are some applications under the random oracle like class. And another application is as a compression function. So for example, in Merkle trees, we are also extensively using hash functions, but there we're using the compression property of the hash function. So we want to compress, to hash together two elements or more into a single element in the Merkle tree to compute proof of set membership. So just some just a list of some of the applications. Any comments?
Like where would a ZK rollup fits here? Would that be like a mix of, like, I guess it uses signature schemes, also prove knowledge of preimage, or
Yes. For a ZK rollup on layer 2, you would be processing, so batching some transactions, and you're processing them, and then you want on layer 1, you want to send just a proof that you have correctly processed the transactions, as opposed to sending all of them on layer 1 to be processed, right? So I think the hash function in this case comes into this box where you prepare the proof that you have correctly batched your transactions. And how do you prepare the proof? You have different protocols for them. For example, Plonk is one ZK protocol that you can use to prepare this proof. And there you would be using a hash function for one in the Fiat-Shamir heuristic, where you're hashing the transcript. Also, yeah, so that's one thing, preparing the proof. Besides Plonk, you may have other proof systems. And another application would be in the Merkle tree, I think, where you're structuring all your transactions in a Merkle tree, right? And then you're giving the root of the Merkle tree. And if you want, on L1, if you want to prove that the transaction is part of the tree, so it is included in this batch, you need to provide the path of this transaction to the root. And to verify the path, you need to be hashing all the leaves on the path, right? You take pairs and pairs and pairs, and you hash them all the way until you reach the root. And this hashing is performed exactly by the second application. The second application, the compression function of you can use a hash function essentially. Does this make sense, Luca?
Yeah, it does. Yeah.
Okay. Yeah. Thanks. So a bit of high-level overview of ZK-friendly designs. So in the past years, it's been a very active area of research, and many new designs have been proposed, literally maybe in the past 5 years or so. And here I'm borrowing a slide from a very recent talk at Crypto 23 by Markus Schoffenegger, so I don't know if this taxonomy is his, maybe he himself cited it from somewhere, but he basically divides the zero knowledge friendly designs into 3 classes: type 1, type 2, and type 3. So type 1, low degree only design. So these are hash functions that will be using only low degree transformation, like this power function x cubed, in order to achieve its non-linearity. So later on, when I show some concrete designs, you get a better idea where does this fit inside the design. But what matters here is that you are using those kind of power maps of low degree. Now, this is very efficient because computing the cube of x in a finite field will not take too much operations, 3 multiplications, right? Even two actually, right? X squared and then again x. So it's very fast. But the drawback is that you need many rounds of this. Again, as I show you a concrete example later on, you'll see what I mean. But you need to iterate this operation multiple times in order to accumulate sufficiently high degree of the final polynomials, that describe the output. So you want them to be of high degree in order to prevent attacks, algebraic attacks in particular. So these kind of designs take a lot of rounds. And because of this, they also will be represented by a lot of constraints. Since you have many rounds, you describe them in your, for example, R1CS trace, and you end up with a lot of constraints. And designs of this type are Posidon, Posidon 2, Neptune, GMC. Then in the type 2 group, we are using polynomials of high degree. For example, x to the power 1/3 in a finite field. This will be a large degree, so it will be expensive to compute. But those designs are using what is called the non-procedural property of these computations, meaning that here in ZK proofs, we need to do verification, as I showed earlier, meaning that this is a situation in which you know both x and y, and you want to verify that x and y are respecting a certain computation. So y is the output of the computation given x as input. And in that case, because you know both x and y, if you have this kind of expensive computation x to the 1/3, you may equivalently transform it into x equals to y to the cube. So instead of checking whether y is equal to x to the 1/3 and computing x to the 1/3, you may instead raise y to the power of 3, which is much cheaper, and compare it against x. So those type of designs use this approach. They are slow because when you do the computation as opposed to verification, you still need to compute the high power polynomial. But because it is of high power, you quickly accumulate a very high degree polynomials, and because of this, you need fewer rounds, and consequently also fewer constraints. And designs of this class are Friday Rescue from the Marvelous Design Strategy and Griffin and Anemoy, which were very recently proposed. And then type 3, these are designs that are using lookup tables. So instead of performing this expensive computation, in particular x to the 1 over some power, they pre-compute a table of such values, and they directly query the table when they need to perform some computation like this. So these designs are fast because querying the table is like order 1 operation. Here we need even fewer rounds, but then the designs of this class are not so flexible because they tightly depend on the scheme that is using them. For example, reinforced concrete is an example of this class, and it has been specifically designed for Plonk. Doesn't mean it cannot be used with other proof system, but if you need to use them with other proof system, you need to well, not to redesign it, but to modify it in a certain way. So those are less flexible to use. So I will give you, in the following slides, I will give you examples of type 1 and type 2 designs, and I will not be looking into type 3. Any questions, comments?
I have one.
Yes, one.
Sorry about that. So this ZK-friendly designs, this is only about, this classification takes into account only hash functions.
Yes. Yes.
It does not take into account some other, whatever, I don't know, not systems, but
Ciphers, for example, or
sorry?
for example, ciphers, you mean like a ZK-friendly block cipher or something like this? Is that what you mean, or?
Yeah, I don't know what I mean. I want to say that it's really only about hash functions.
Yeah, yes,
nothing else that can be used, like, you know, in a proof system. So nothing else is classified here.
Yes, so this taxonomy is specifically for hash functions. That's true. So maybe the title is misleading. So ZK-friendly hash functions, it should be more appropriate to say. Yes.
I mean, you only gave examples as hash functions, but I wanted to make sure. And
Yes.
then another thing, I mean, this is quite interesting. I think this taxonomy is very interesting, but just to make sure that I understand how fast, slow, and very fast is, because to me, type 1 and type 2, in the end, you said, correct me if I'm wrong, so you have a lot of these low degree powers, for example, for type 1, but somehow you end up with a high degree in the end, or a large polynomial, but large polynomial means what? Lots of terms of low degree. That's how come it's still fast. And for the type 2, like, how come it's slow? Because it's like the same power that you had in type 1. Sorry if that makes sense.
Yeah. So for type 2, so we need to distinguish between computation and verification. So when you are computing the hash, so you're given x and you want to compute the hash of x. So in that case, you don't have the luxury to do this implication here. You cannot do this trick, like, because you don't know why. So in that case, you are constrained only to this computation. So you need to do this high power computation when you compute the hash for type 2. And for type 1, you just are doing the cube. So when you compute the hash, there is no escape from this high power. Now, when you do the verification, you are already given y. So then you can make use of this. So then verification is fast. So
Got it. How about all right, how about then the many rounds in the first type and the fewer rounds in the second type?
Yes. So for example, it can be a factor of even 10. So it can be quite drastic. For example, for type 1, again, citing from memory, but Posidon has many rounds, maybe something like 80 or something like this. While here for type 2, we're working with order of 10 rounds, 8, 10, 12, something like this. So you're between 80 and 10. So that's how big the difference is in terms of rounds.
And the many rounds compensate for the fast computation, and the fewer rounds or the fewer rounds compensate for the fact that it's slow, and overall like get the same security level, sort of.
Yeah, more of the second. So the many rounds compensate for the slow increase of the degree, because you increase the degree by 3 at every round. So you have first x to the 3, then x to the 3 is pushed to the next round, and it becomes x to the 9, x to the 12, and so on. So the degree increases relatively slowly. And that's why you need many rounds to compensate for this slow increase in the degrees. While here, already after 1 round, you have a very high degree, and after 2 rounds, even higher. So then you need much less number of rounds to achieve the same degree in the final polynomials.
Okay,
Yeah.
cool. I'm looking
Yeah.
forward to examples. Thanks a lot. This made a lot.
Yeah. Also, you made another point. What does it mean to have polynomials of high degree? And it's a good question. I think it has, like, there are several perspectives. One is you want the highest degree monomial to be high enough, but you also want to have sufficient low degree monomials to prevent like different types of attacks. So you care about both.
Cool. Looking forward to more examples and probably more questions.
Yeah, sure. So we're 26 past. We have about 15 minutes. So I am moving. Is this tempo good for you? Because I think okay, perfect. Yeah. So I shouldn't worry that we will leave material that's not covered. We can cover it later. Okay. So here I will give you examples of type 1 and type 2 designs. And the first one is Memc. It's arguably one of the first, if not the first, arithmetization-oriented hash function targeted specifically for advanced cryptographic protocols. I believe it was proposed for multi-party computation initially. And it's a very nice design to start with, because it's basically as simple as you can go for designing a ZK-friendly hash functions. So what you see here on the picture is a sequence of rounds, where one round is a sequence of operations like this. You have XOR, so this is exclusive OR operation, and you have the cube, this power sum, the cube of X. So those two operations compose one round, and you have a sequence of those rounds. So you iterate the round function multiple times. Now, this XOR, which is, you can think of it as a linear layer, so a linear operation, it XORs the round keys before the application of the cube function. So broadly speaking, you can think of this as a linear layer followed by a nonlinear layer, a linear layer followed by a nonlinear layer. So linear transformation, nonlinear transformation, linear, nonlinear. And the linear transformation absorbs the key material into the state. And beside it, it also XORs a fixed constant, a public constant, which serves the purpose to make the keys different for the rounds. Now, what are the arguments that this is good with respect to security? The trick is in the power map. So this X-cube power map has been analyzed many years ago. So there is a seminal paper dated, so two of them actually, 93 and 95, by Nyberg and Nyberg-Knudsen. So in particular, the second one, Nyberg and Knudsen, they were analyzing this power map, x going to x to the 3, and they provided actually a general description, which is x to the 2 to the power of k plus 1. So for with the restriction that k should be greater than or equal to 1. So if you set k to 1, you end up with the smallest possible power, which is 3. And then in this paper, they prove, again, in quotation marks, good differential and linear properties of this mapping. And remember, this was done in the years when we dealt only with like classical cryptography, so symmetric key cryptography. And in this world, the main attacks that we care about are differential and linear cryptanalysis. So these are the most powerful attacks, and many variants of them were devised after that. But the point is that we have quantities that can measure a mapping, can measure the security of a given mapping with respect to differential and linear attacks. So for differential attacks, we have the differential uniformity, and it's a quantity that you can exactly compute. And for linear property, we have the linearity of the mapping. And it's again a quantity that you can precisely measure involving the Walsh transform. So for this mapping, in this paper, they proved that this cube function has high differential uniformity and high linearity. I mean, high coefficients of the Walsh transform and high properties of resistance against differential attack. So interestingly, 2 years before, the similar result was proven for the inverse mapping. So x up to x to the -1, so the modular inverse in a finite field. And this mapping was adopted as with like a small modification as the main component of the AES S box. So it's kind of interesting that you have this x to the -1 adopted in the most widely used symmetric cipher nowadays, and later on we have the second mapping, which is x cubed, adopted in probably the first ZK-friendly hash function. But okay, so that's the reason why x cubed is an interesting mapping. So it has provable properties against differential and linear attacks, and to make it resistant, to make the design resistant against algebraic attacks, we just need to add sufficient number of rounds. So much for the Memc design. Any questions on it?
I feel like a security tool, maybe that's too much for like the hash function. So besides this for power mapping, yeah, I don't know how you do, like how you test the resistance of a hash function to various.
Yes, yeah. So basically, you do the best you can. A short answer, but what you do in practice is actually apply different known attacks to the construction, show how many rounds they break, and then kind of semi-heuristically add a margin of additional rounds, and then claiming resistance against this particular attack. And then you do this for the most common attacks. So for ZK designs, this would be algebraic attacks. So you mostly care about Grosvenor basis and some other variants like interpolation attacks and things like this. But the approach is really to apply the attack and see how many rounds it breaks, and then add sufficient more rounds to resist it. Unfortunately, we don't have security proofs for, you know, unconditionally proving that yes, this is secure. We can go as far as proving some nice property about the nonlinear mapping, which is a crucial component in every design. But beyond that, it's really about applying an attack and showing resistance to it.
Very cool.
So another type one example. So I think we have probably about 5 minutes more. So I think I will end up with listing all the like ZK-friendly designs, and we can wrap up there. So another type one example of a ZK-friendly hash function is Posidon. It's widely used nowadays. I'm sure, like, if you've done audits of code bases, chances are that you must have encountered it at least as a name somewhere. Now, this design, it takes, I mean, conceptually, you can think of it starting from Posidon and adding a bit of complexity to it. So in particular, its main nonlinear component, the S box, it's still the cube power mapping. So they still use the X3 power map. But the overall strategy is applying the substitution permutation network structure of the AES. And in this structure, well, with some modification. So in this structure, we have a sequence of rounds that are iterated over the computation, and every round is composed of three operations. So the first one is add round key or add round constant, depending on the constant, on the context. The second round is the nonlinear round that applies a layer of S boxes on smaller chunks of the state. And the third round is linear transformation. So you have substitution, permutation, substitution, permutation. The permutation would be the linear transformation. So this is the SPN structure proposed with AES, and Posidon uses it, but it makes the following modification. It introduces a new type of internal rounds, if you notice here, which do not contain a full layer of S boxes. So in the internal rounds, only some of the wires pass through the nonlinear transformations, while others are just copies. Now, this saves on efficiency because remember the cube mapping is the efficiency bottleneck in terms of constraints, especially when you have a lot of rounds. So think of this like 80 or something like this round. So they propose not to apply the S-box layer in all places, but in some places this saves a lot of constraints. But at the same time, it still contributes to the nonlinearity. So you still achieve some increase of the degree of the polynomials. So broadly speaking, they have a sequence of top rounds that are with full nonlinear, a sequence of both rounds full nonlinear, and intermediate rounds with only partial nonlinear layer. And they generalize this as a Hades design strategy, and then Posidon is just one instance of this design strategy. Any comment on Posidon before I move to the third and last highlight of the ZK-friendly designs?
Yeah, one question. This looks, and as you've mentioned, very similar to what they do when they encrypt with AES, for example.
Yes.
This substitution permutation. What makes it ZK-friendly then? What's the problem with ZK first? Is it just performance? So you need to work in context of how ZK works, like optimize for it? Or there's something else that needed to be adjusted?
Well, yeah, like I showed in one of the first slides.
Sorry. I was late.
Oh, you were late. Okay, let me quickly bring back this to you. I think it's an informative slide. So you see, that's on the left. You see the classical designs AES, and on the right you see arithmetization oriented. So what I was saying is that in classical designs we work over a binary field of small size, so 2 to the n, where n would be 4 or 8, with chunks of 4 or 8 bits. But here we work over finite fields of huge size. So Q would be 2 to the n for n bigger than 64, and P would be a prime number, for example, for BLS 12381, this huge prime number. So one issue is that you are handling huge finite field elements as opposed to to bits. And the second thing is that you need to optimize for constraints, like this was on this slide, where I was saying that the metric that we try to optimize against is the number of constraints that represent the circuit corresponding to your hash function. And for example, for R1CS, a constraint is counted as a multiplication. So you want to have as little multiplications as possible. So that was making a difference. And if you go back now to Posidon, like what you were saying, what makes it different from AES, well, you have here the S box as the cube mapping. And this is efficient in terms of multiplications, in terms of multiplicative constraints, like x cubed is x times x times x. So you're performing 2 multiplications, 2 constraints. In contrast, the AES box is the modular inverse, x to the minus 1. So in a finite field, x to the minus 1, especially finite field of large size, x to the minus 1 will be huge power. So you will be performing like hundreds of multiplications for it. So that's what makes it different.
Yeah, I see. Thank you.
Yeah.
And I will watch the recording. The first part.
Okay. Yeah, sorry for the other guys if I repeated something. Yes, Gianfranco?
Yes, I want to answer each of the chunk of that passes through the no linear layer. Is it a field element or is like chunks of a field?
Yeah,
Okay.
yeah, it's a good question. In this case, it's a field element, yes, because you need the power mapping demand
Okay.
this. You need
It-
X to be such an element. But for other designs, you may have like a vector of field elements that are processed. In particular, in our design, in Anemoy, you have a vector of 2 field elements that are sent to the S box, and it produces a vector of 2 other field elements.
And how, like, because the input of the hash function is a single one file element, how is this file element split in?
Sorry, again?
I mean, the input of the hash function is
Yes.
a single one file element, right?
It can be any number of
Okay.
elements.
Okay.
So you can have a unlimited
Okay.
size vector of field elements, which you hash into something fixed.
Yeah. Okay.
Okay, so the last highlight that I wanted to show from the ZK-friendly design is the first instance of the type 2 designs, which is rescue. And rescue, if you remember, for type 2, we are using both. We are still using the power map x to the alpha, but we also use its inverse, x to the 1 over alpha. And that's what the rescue designers do. Again, conceptually, you have the same idea of like non-linear layer followed by a linear layer followed by a key addition. So that's one round for you, and then you iterate it. But here they have 2 types of S boxes. One is the x1 over alpha, which is the inverse, so a high degree polynomial, monomial in this case. And here is the second type of S box, which is a low degree monomial, so low degree power map. Now the benefit of this design strategy is that you still use the high power map, thus quickly increasing the degree of your polynomials, but at the same time you are mixing it with low power map, which is efficient to compute. So you kind of try to take the best of both worlds. And also when you do verification, that is in the non-procedural setting where you can compute both forward and backward, you can always actually be using the low power map, right? Because then you just transform x to the 1 over alpha into y to the alpha and just checking whether x and y match. It still uses the SPN structure, then alpha, ideally it should be 3, but it depends on the modulus of the finite field. So we need an invertible map. So for some fields, you may need to have 5 or 7, but usually 3 or 5 works. So this is the rescue design. We have 2 more minutes, I think. Do you have a comment on rescue? A question?
No, sorry. When I'm thinking, I touch my head. Sorry.
Okay. Yeah, so I was actually expecting a question from you, because like we're talking about hash functions, right? So when in a hash function you have some unlimited size input and you're producing a fixed size output, and all the transformations that I just showed to you, if you notice, you have same size input going to same size output, like right? For Memc, you have a single element, you produce a single element. For Posidon, you have like, I don't know how many, 16 or whatever inputs, you produce 16 outputs. Similarly for rescue. So you don't achieve any compression. You don't do any hashing, right? It can be encryption at best if you have random keys, or it can be just some permutation at worst if the keys are public, like public constants. So I was wondering if you would ask me, so where does the hashing come in? Do you have an idea? Yeah, okay. So that's an important part because it's extensively used, and we also use it in our Anemoy design. So that's the sponge structure, and that's what is used in the catch-up hash function. So essentially, the sponge structure is a nice way to turn a public permutation into a hash function. So what you are seeing here, so you have a public permutation f that is iterated multiple times. And in the very beginning, you have input state, which is public, so it's a known value. Typically, it's 0. And this public state is divided into two parts, the rate and the capacity. So the rate, okay, before speaking about the rate and the capacity. So what happens, you start with some input here, and then you are breaking the message that you want to hash into appropriate size chunks. So in this case, we have 4 chunks of those. And each of them has the size of the rate. Each of them is of size r bits. And here, you just propagate, you just copy the output. Then you feed this into the permutation. Then the output, you XOR to the next message chunk. Here, you just copy the output, and you go on like this. And this whole phase is called the absorbing phase because it keeps consuming the message blocks. So the message blocks are absorbed into the internal state of the permutation. And then at some point, after you have processed all of your message blocks, you start squeezing the state. And in this squeezing, you start outputting blocks. So Z0, Z1, Z2. And these blocks will be your hash. And you will be squeezing as long as you want your hash to be long. So in this case, the hash is equal to three field elements, for example. Now about the rate and the capacity. So I'm sorry, we're a bit over time, so I'm finishing very soon. So the rate determines the speed in which you will be processing your message, because the larger the rate, the bigger the message chunks, so the faster you will consume the message. But conflictingly, the capacity determines the security of your hash function, because this part here will not be known by an attacker. So you want the capacity to be as large as possible for security, but you want the rate to be also as large as possible for high throughput. But to put the long story short, in this structure, simply replace this small f permutation by any of the listed designs. So simply put Memc here, or Posidon here, or Rescue here, or Anemoy here, and then you have a hash function. So that's the idea of the sponge structure. It turns a public permutation into a hash function. So when you design your hash function, you need only to focus on designing a good public permutation f. Any questions, comments on this?
So overall, actually, what you have shown before, it's not a hash function. Yeah, it's just this permutation. So a hash function is the sponge structure plus the public permutation.
Yes, correct. Yeah, but because this is really the meat of the design, then you plug it into this like generic structure, and then you have your hash function.
And from the modern or ZK-friendly hash functions, what does not follow this sponge structure? What does not use? Like not all of them, but like say some very famous and.
Oh, you mean some designs that don't follow the sponge structure?
That we have heard of.
Yeah, so it's a good question. I'm not 100% sure. I think most of them do it, but maybe some of them, even those that have the sponge structure, they also propose a variant in which they don't use sponge but use a Posidon network. So a case in point may be Memc might be one such design, but that's to be checked. Griffin, this new design, I believe it also uses, at least it has a variant with the Posidon network, or again to be checked. So these are the ones that come off the top of my mind. For Anemoy, we're using the sponge structure in our hash function, but we also propose a variant used only for compression that does not use the sponge structure, the jive mode of operation.
So it's either sponge structure or the Posidon network. Most of them are into this sort of design.
Yes, but now come to think of it, I mean,
Approximately.
even if you use Feistel, I mean, you cannot use just Feistel for hashing. So now I'm thinking about this. Even the ones that use Feistel, maybe they use the Feistel just to design their permutation, and in the end they still plug it into the sponge. So it's a good question. I would be interested to check more precisely, but it seems to me it's like maybe 99% use the sponge structure. Because the other alternative in the classical world besides sponges, what we have before the sponges was the Merkle-Damgard construction, where you have a compression function and you iterate it, and you, like the output of the previous iteration, you feed it into the input together with the message block. So that was the alternative way to design a hash function. And then the sponge was proposed, and now it seems like the dominant strategy for designing hashes. So maybe 99% maybe actually use the sponge.
Thank you very much.
Let me quickly, yes. So I'm happy to talk as long as you are available. But just to like formally close what I wanted to say. So I think we can stop here with the new material. So from my original plan, I think we covered point 1, which is not bad because it's kind of a self-contained content. And what remained is oh no, sorry, 1 and 2. Yes, actually 1 and 2. So what follows is section 3, where I can dive more into the details of anemoid, and I think it will be easier to follow now that you have a broad background and context of like what does it mean to design a ZK hash function. So if there is interest in the future, I'll be happy to schedule another talk on this. Now that being said, I'm still available, so if you have questions or would like discussion on some points, you're very welcome to say.